All right, so today we are going to introduce an idea that will help us to count appropriately when we're dealing with atoms. Um, Atoms, because they are so small, are difficult to count by traditional ways. Um, you don't necessarily need to write this down, but let's just think about it for a minute. There are several different ways to measure or account for items. Number one is just by number. Okay, I count the students in here 1, 2, 3, 4, 5, 6, 7, 8, 9. Better just stop. Okay, and you can just count the number. All right, and there they are. We could also do that by mass. So we're using apples here for this example. So if I had 10 apples, that also could be represented as 1 kilogram. And we could talk about it in terms of the mass instead of just the number of individual apples. A third way to discuss that would be in terms of volume. Um, we don't usually talk about that too much, just in our everyday usage. This might be something that's going to be more common in certain agricultural industries. Um, but if you've got, a bushel is about the size of a medium laundry basket and would contain 35 liters or 35. Hold that up, Grant. That's a liter. There you go. There's a liter. And so that's a 1 liter water bottle. And 35 of those would be considered a bushel. So your nice basic bushel basket. All right. So we could talk about objects in terms of the number, in terms of the mass, or in terms of the volume. Now, let's say though that we want to apply that to atoms. Okay. Mass of atoms. Okay, like carbon. Can I mass out a certain amount of carbon? Absolutely. All right, so I could get out a pan balance and mass out 17.2 grams of carbon, no problem. Volume, I could get out my graduated cylinder and I could dump the carbon in there. That's going to get a little messy, but I could do it. All right, 4.1 milliliters of carbon. Counting. And then I'm like, hey, I'm going to need a lot of atoms. I'm going to need like 45. Could you count me out 45 atoms of carbon? And the answer is nope. Because even if you could see the individual atoms, which you can't, they are way too small, we don't have a way to, and what are you going to like straighten out a paper clip and, kind of scrape the atoms across from one side to the other? No, I mean, that's way too huge for atoms. Atoms are on such a small scale that we really just can't even comprehend it. So how do we count individual numbers? All right, and that's where we need a different counting unit, and that's going to be the mole. It's going to come in. It's going to come into play for us. What I want you to understand about a mole is, even though it's a specialized number, it's really just like a dozen, except a different number. So the mole is a counting unit, just like a dozen is 12 of something. A gross is 144, 12 12s. Okay. A mole is 6.022 times 10 to the 23rd items. Hey, so here's what I want you to. All right, and so the mole, just as we said, that a dozen is 12 items and a gross is 12 12s or 144 items. A mole is literally 6.022 times 10 to the 23rd items. Now, that is not 6.022 times 23 or 6.022 times 10 times 23. That is literally 23 zeros. That is moving the decimal place 23 places to the right. And that is literally this many items. So if you had that many eggs, you're like, hey, a dozen eggs. I'm going to go to the store. Do you need something? And your mom's like, yeah, get some eggs. And you're like, a dozen or a mole? She's like, whatever. And so you come home with a mole of eggs. I'm not sure that many eggs have ever in the history of the world existed. Okay? Hey, I want to put this in context for you guys. An item that's incredibly big that we sometimes hear about is our national deficit. Which is currently running in the trillions. It's currently running in the trillions. It's something that's big. Now let's see. This is hundreds. This is hundreds of thousands.
It's frozen.
Oh, thanks. Oh, that's what you. Okay, all right. Yeah, I didn't understand anything you said at all. Okay. Oh, look, there we go. So it is literally that many items down there at the bottom. Now, again, the national deficit. If we talk about that, there's hundreds, 100,000s, millions, 10 million, 100 million, billion, 10 billion, 100 billion, trillion. So this is where we get into the trillions. And let's just say that it was 99 trillion something. Here's what I want you to see. That would be this many things. A mole is then still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more orders of magnitude larger than that. So you almost need a trillion trillions before you get to where a mole is. All right? So just try to conceptualize that. That is a lot. Here's the thing, though. When we're dealing with atoms, they are so small that it takes a lot of them before you get to any appreciable amount that you can, really deal with in our macroscopic world. And so that's what the point of that is. So it is a mole, which is that many items, is defined as the number of atoms in exactly 12 grams of carbon-12. And that was determined experimentally thanks to Amedeo Avogadro, who's probably French, so pardon my French with that. So 12 grams of carbon-12. In other words, if you have 12.00 grams of the isotope carbon-12, you have this many atoms. All right. So 12 grams. Now 12 grams is kind of a reasonable. That's like if you rip open a hot chocolate package and you've got that much powder inside. That would be close to. If you had maybe 2 hot chocolate packages, that would be about 12 grams of carbon. So when you have that much carbon, you actually have that many atoms of carbon. Just something, curious and interesting to think about. I don't care necessarily that you write down that huge long number. I do care that you know that the definition actually came from the number of grams of carbon-12, and that a mole is equal to 6.022 times 10 to the 23rd. And if you can just remember Avogadro's last name. By the way, this number then is referred to as Avogadro's number. So that is Avogadro's number. Shape that A up a little. All right. And that is that. We're ready to move on? Okay. So the question before us is, how many moles of phosphorus are in this many phosphorus atoms? So I want you to remember back much earlier in the semester when we talked about conversions, and we used something called dimensional analysis. All right, I'm just going to make you motion sick doing the screen up and down while I try to get it just right. Hey, do you remember when we used dimensional analysis? We would take whatever we were starting with, we would, draw the great big long line, and then we would section it off. Okay? So, all right. So we would take that great big long line, and then we would section it off. And then in each section, we would write equivalent units. And that would allow us to convert from one thing to another. So I want to look at this real quickly before we actually do the math. Remember to always put what you're starting with. So your starting quantity goes right up here. Now, if it has a per in the units, like meters per second, then you would put the meters on top and then the seconds on the bottom, because per literally refers to the dividing line. All right? And then for each little section after that, we have equivalent units or equivalent amounts or equivalent quantities on the top and bottom. And that's because if you have equivalent amounts, you are actually dividing by 1. Okay, if I have something divided by itself, that's a value of 1. And so then when I multiply something by 1, I'm not actually changing its value, I'm just changing its unit. All right? And so that's the reason that we are able to get away with that mathematically and have it still be legit. All right, so with that in mind, let's look at, we started with this many phosphorus atoms. All right, so that was our starting point. And so we said, hey, I've got this many phosphorus atoms, 1.20 times 10 to the 25th. And I want to convert that into moles. So the question is, how many moles of phosphorus? And that is what I'm looking for. All right, so I need to transition from atoms of phosphorus to moles of phosphorus. And the way I'm going to do that is I'm going to use anytime you're going back and forth between moles and atoms, you are going to use Avogadro's number as the conversion. Avogadro's, not avocados, Avogadro's. Avogadro's hashtag. No, Avogadro's number. So you will use that anytime you're going from moles to atoms or atoms to moles, because that lets you know how many atoms are in 1 mole. How many? 6.022 times 10 to the 23rd. All right? So I have this many atoms of phosphorus, and I'm going to convert that to 1 mole of phosphorus. And so when we convert to moles, we're going to multiply by, not multiply by, we're going to put, since we've got atoms of phosphorus on top, we're going to put atoms of phosphorus on the bottom so that they will divide away. And since there are 6.022 times 10 to the 23rd atoms in 1 mole, we'll have the equivalent value, 1 mole on top. Remember that what we're really doing is we're multiplying all the way across the top. So I've got x times y times z, times whatever, and then divided by whatever's on the bottom. T times u times v. All right? In this case, it's 1 times this on the bottom, and it's 1.20 times 10 to the 25th times 1 on the top. Okay? Questions about that? So we multiply the top, we multiply the bottom, then we do the division. You have to be really careful with your order of operations so that your calculator doesn't mess things up for you. All right? Why don't you do the math real quick just to confirm that you are putting the numbers in the calculator and see if you get something around 19.9 for your answers. All right? Just try that out real quickly. So did we all come around to 19.9 moles? Yes, yes? All right, excellent. So I would like you to try one on your own. So remember so I'm going to work also, but you go ahead and try this on your own. Remember that what we're going to do is we're going to start with, it says how many moles of magnesium. So that's going to be our finishing point. That's what we want to finish with. And our starting point is this many magnesium atoms. So I'm just going to write that. So that's our starting point. So I'm going to write that here. 3.01 times 10 to the 23rd magnesium atoms. All right. I'm sorry? Does it say to the 22nd? My goodness, to the, 22nd. Yeah. 22nd, that's a 2. Magnesium atoms, thank you, ma'am. Now, again, since we're going between moles and atoms, and it doesn't matter which way you're going, you're either going to multiply or divide by Avogadro's number. All right? So I'm going to look at this. Now, I've got number of atoms on the top, so I need to put number of atoms in the denominator in order for that to cancel. I know that there are 6.02 times 10 to the 23rd magnesium atoms in 1 mole of magnesium. And so at this point, magnesium atoms cancels, and I'm left with just moles of magnesium, which is where I want it to be. So I will take this, multiply by 1, and then divide by Avogadro's number, and that looks like that should get me somewhere around 0.05. Okay, approximately 0.05. About 0.05 moles of magnesium. Just check it out and see if you get something in that range. All right, excellent. We've got that there. We're ready to move on. So let's do this one. It is the same, except instead of going from atoms to moles, we're going to go from moles to atoms. So we will. So this time. Well, here's what I'm going to tell you. I'm not going to answer that. I'm going to tell you to write it down in the dimensional analysis frame. So write it down in the frame. All right. I'm going to give you just a second to do that, and then I will scroll up. Look and say, what am I starting with, and what do I want to finish with? You want to finish with how many atoms of zinc, and you're starting with 0.750 moles of zinc. And so if you scroll that up, you will see that once again we put our starting value right over here. Starting value right here, 0.750 moles of zinc. And then we put 1 mole. That atoms really should be right there. It sort of got kicked down. Stupid PowerPoint. Kind of got kicked down the wrong way. 1 mole of zinc atoms, so that our moles will cancel. Mole of zinc, and then we're left with number of atoms. And so, Charlie, your intuition was correct. We will, in fact, be multiplying and come out with something around 4.52 times 10 to the 23rd zinc atoms. Everybody try that out. See what you got. All right, so we'll celebrate our victory there, and we will move on to the next one, which I will let you do on your own. How many atoms of gold are in 8.50 moles of gold? All right, so I randomly found 8.50 moles of gold in one of the lab drawers that apparently a former pirate had left there. And I said to myself, hey, wonder how many atoms that is. So how many atoms of gold? That's what we're interested in. That's going to be our finishing mark. 8.50 moles of gold is going to be our starting point. So I'm going to start with 8.50 moles of gold. my line in there. And I'm going to need moles of gold to cancel. So I'm going to put it's in the numerator, so I need to put it in the denominator. And I know that 1 mole of gold is equivalent to and then I will multiply through there and get a number of atoms. Somebody let me know when we get a value. All right, what do you have? I was about to say, I'm not feeling like that's going to be correct. There you go. I think that's okay. 5.1 times 10 to the 24th atoms of gold. All right, and so there we go. By the way, I did the math on that earlier, and I think that's going to be around $60,000 worth of gold. So somewhere between $60,000 and $70,000 worth of gold, just rough guess. Just in the drawer. You know. Oh no, that's not a bar. That's a bar of gold. Actually, that might be. I don't think that's a bar of gold, because a bar of gold. This is about 4 pounds worth of gold. And I think a bar is going to be more than 4 pounds. I think it's. Well. All right, so we have figured out that actually at today's prices of almost $1,800 an ounce, that would be close to $125,000 worth of gold. Yay me! So that is the deal for that. So let's continue on in our discussion of moles and dozens. So here's what I want to ask: a dozen is a dozen, right? You have a dozen eggs, you have a dozen elephants. Same? Yes, yes? Yes, Delaney? Yes. No? Well, no, it's not the same item. Hey, here's what I want you guys to think about. So, a dozen eggs, 12 eggs. A dozen elephants, 12 elephants. I decided that I would like to take a dozen eggs over to Nacogdoches, to one of my friends over there. And so I load up the eggs in the Jeep, just right there in the front seat next to me. Off we go. Be there in 25 minutes. And I decide also the next day that, he liked the eggs so much, I want to take him another gift. And so a dozen elephants. And so it seems like a thing to do. So, yeah. And then I realized this is going to be a much more serious endeavor to transport a dozen elephants to Nacogdoches. Hey, here's what I want you to understand. Yes, they're equivalent. 12 is 12. But at the same time, they're not, because they're very different amounts of mass involved. Okay, so not every 12 is the same as every other 12. All right? So, yes, they're both 12, but no, because the elephants weigh way more. So it's the same.
Then you're not talking about the dozen. You'd be talking about the eggs and the elephants themselves.
But aren't they still both a dozen?
They're still a dozen, but the dozen isn't.
But
It's
aren't
not
they?
what you're referring to when you refer to an elephant.
Aren't they still a dozen? Aren't there still 12 of them?
Numbers, yeah.
Yeah. Okay, so it's the same number, but different amounts of mass. Yeah, I know. I feel like that we're saying the same thing here at this point. Hey, so here's what I want you guys to understand. It works that way for atoms as well. 1 mole of carbon atoms, 12 grams. 1 mole of uranium atoms, maybe a little more. Okay? Because you guys understand that not all atoms have the same mass. All right? They're not all the same size. Why not? Why would atoms be different sizes? Yeah, specifically protons and neutrons. The electrons are almost weightless. Um, one electron is about 2,000th the mass of a proton. So you have to get 2,000 electrons somewhere before it weighs as much as a proton does. So really, it's basically the protons and neutrons. All right. Hey, carbon, 6 protons, 6 neutrons. Yes, yes. Okay. Uranium, down here around 92. Let me find it. There it is. So 92 protons and a lot more than that neutrons. Okay, totaling out at 238, mass of 238. Hey, so clearly an atom of uranium has a lot more mass. So there's my eggs and my elephants. Okay, not literally, but I want you to understand that a mole of carbon is not going to have the same mass as a mole of uranium, right? Even though they're both a mole. Yes, yes? Yeah, I know, kind of dry, but we're moving on. So I want you guys to copy this down exactly as it is. 1 mole of helium atoms and 1 mole of carbon atoms are both that many atoms. However, the carbon is going to have a mass of, actually don't, yeah, go ahead and copy it down. Go ahead and copy it. All right, so what I want you to understand about this, yes, they're both 6.02 times 10 to the 23rd atoms. However, 1 atom of carbon has an atomic mass of 12, and 1 atom of hydrogen only has an atomic mass of 4, and so the mole of carbon will actually be around 3 times as much. All right, so let's press on. All right, so what we can see is that even though 1 mole will have the same number, they will not all have the same mass. And so I want you to write down that the mass of 1 mole is what's called an object's molar mass. Due to the boundless creativity of scientists, let's see, let me wake this thing up. Oh, and my tablet picked that moment to run down. All right, so again, the mass of 1 mole of an object is its molar mass. In other words, how much does 1 mole of that object have? What's the mass of it? Again, the definition of 1 mole of carbon-12 is 12.00 grams. And so that would actually be, so 12.00 grams would actually be the molar mass of carbon. All right? So however much mass 1 mole has, that's the molar mass. There we go. So, yes, as we just said, 1 mole of carbon is exactly 12.00 grams of carbon-12. Molar mass of that is 12. And the molar mass in grams for any element is equal to its atomic weight in AMU. So I do want you to write that down. In other words, if we look on the periodic table, whatever the atomic mass is of an element, that is also its molar mass in grams. So I look on the periodic table and wow, calcium, it's 40.99 maybe, or 40.08. So calcium, 40.08 is its atomic mass. That means 40.08 grams of calcium will have exactly 1 mole of calcium atoms. All right, so I want you to be sure that you've got that second arrow written down, that the molar mass in grams is equal to its atomic weight, and that's going to be equal to 1 mole of atoms of that material. All right, so that means, let's just talk about a couple of our favorite elements in here. Delaney, favorite element? Neon. Okay, so Delaney, tell me the atomic mass of neon. Yeah, like from the periodic table. You could use, yeah, I was about to say, you've got one right there, don't you? All right. I'm going to come back to you. Ben, what's your favorite element? Oxygen. Oh yeah, I'm loving my oxygen. That's an excellent choice, Ben. Hey, so I want you to look and find out what the atomic mass is. All right, Delaney, what'd you get for neon? 20.179. That means that if I had 20.179 grams of neon, that would be 1 mole of neon atoms. Ben, what about oxygen? The atomic mass. Yeah, 15.999. So if I had 15.999 grams of oxygen, I would have 1 mole, 6.02 times 10 to the 23rd of oxygen atoms. All right. Chanel, favorite element? Chlorine or fluorine? Chlorine with a C. Everybody loves chlorine. Swimming in the summertime. Tell me its atomic mass. 453. Okay. Which means 35.453 grams of chlorine, I would have 1 mole of chlorine atoms. Okay? So that is how that works. All right. And I just want you to add this to what you wrote earlier, that even though your helium was 6.02, 1 mole of helium was 6.02 times 10 to the 23rd atoms, and 1 mole of carbon was 6.02 times 10 to the 23rd atoms. I just want you to add out to the side that that those have a mass of 4 grams and 12 grams respectively. Yeah, not respectfully, respectively. That respectively means in the same order. Respectfully means, kindly and with courtesy. Yeah, so you can have it both respectfully and respectively. All right. And if you want to write down that 1 mole of gold happens to have a mass of 197 grams, you can. All right. Hey, so let's look at this one together. How many grams of nitrogen in 7 moles of nitrogen? Now, earlier I told you that that whenever we went from atoms to moles, that we always use Avogadro's number. Question? That slide? All right. Hey, we were just adding on to something we wrote earlier. Okay. All right, so we're ready to press on. Hey, how many grams of nitrogen in 7 moles of nitrogen? I told you earlier that anytime you go between atoms and moles, you're going to be using Avogadro's number. Anytime that you go between moles and grams, no matter which way, you will be using the molar mass. You will either be multiplying or dividing by the molar mass to make that conversion. So in this case, the question is how many grams of nitrogen? So there's our question. 7.0 moles of nitrogen is your starting point. And so that's your starting point. Hey, notice that there's a little typo here in the PowerPoint. So I'm going to change this to be 7.00 moles, like it says in the question. All right? So I start with 7 moles of nitrogen. I look on the periodic chart. Hey, hear me now, believe me later. This is important for you. Anytime you are pulling a number off the periodic chart, I would like you to use 2 decimal places. Okay? Regardless of the number of significant figures, I just want you to use 2 decimal places. So in this case, that would actually be 14.01 for nitrogen. All right, the PowerPoint is rounded to 14. That will be okay, and we will go with it. Hey, 7 moles times 14 grams per mole, so that my moles of nitrogen divide away. 7 times 14 is 98, because we had that little mistake in the graphic. Okay, questions about that? We're feeling good in the neighborhood? Hey, you need to, if you can remember these things right here, this is a big deal for you, okay? Those 2 conversions are going to be key for this unit, because you will either be going from atoms to moles, moles to atoms, or grams to moles, moles to grams, or you will be comparing number of moles to number of moles. This is going to be a key piece of information for the remaining 10 weeks in chemistry. When I say it that way, it sounds like a long time. Yeah, thank you for those nods of affirmation, yes. It'll zip before we know it, though. All right, so let's move on to our next example. And I want you to see if you can set this up on your own. How many moles of iron are in 74.565 grams of iron? Oh, again, the motion sickness. Mr. Willis, please stop. How many moles of iron in 74.565 grams of iron? Take a moment, choose your starting point, choose your finishing point, and write those down with your conversion factor. So here where it says how many moles of iron, that is clearly going to be my end point. In 74.565 grams of iron, that is my starting point, because that is lets me know how many I have. So I'll start with 76.565 grams in the upper left corner, and then I will put grams in the denominator. And if you look, it says our PowerPoint has chosen to round to whole numbers and be 56 grams of iron atoms. I have told you to choose 2 decimal places, and so that is going to be 55.85 grams of iron. We will still end up with basically the same answer, but it's all good. And hopefully you will get 1.33 moles of iron. Take a moment, be sure that you set that up properly, and hit the multiplication, see that it works for you. All right, so we are ready to press on. We got 1.33 moles of iron atoms. Ooh, but what if it's a compound? What if it's not just an atom? Okay, consider sodium chloride. Hey, how do you think you would find the molar mass of sodium chloride? I'll give you a hint. Find the molar mass of sodium, add the molar mass of chloride, and that will give you together the molar mass of sodium chloride. Okay? And so that is all that there is to finding the molar mass of a compound, is you just find the molar mass of all the parts. All right? So 1 mole of sodium chloride is made up of 1 mole of sodium plus 1 mole of chlorine. 1 mole of sodium is going to be, we said that was calcium. So I think this is going to be 22.99. So let me erase that. All right. So 1 mole of sodium is going to be 22.99 grams. 1 mole of chlorine is going to be 35.45. And that's where I'm stopping. And then I'm going to add that. 9 plus 5 is 4. Carry the 1. 14. Carry the 1. 5, 6, 7, 8. Almost got me. 58.44. And that is the molar mass of NaCl. Okay, grams. And you need to say grams per mole, okay, because it's that many grams per mole of sodium chloride. So that many grams per mole. Sure enough, they rounded to 23 and 35, and it still comes out, about the same, because they rounded 23 and 35, so it would add together to make 58. All right, we feel good about how that happened? Excellent. All right, so let's press on. Oh, the molar mass of a compound is equal to the sum of the atomic molar masses of the atoms. All right, and we did that. Hey, I hear that some of you all, I have heard the whispering, that some of you all are like, I really don't see why it's so important for nomenclature. Mr. Willis just is like, nomenclature, why is that such a big deal? Consider carbon dioxide. Oh, no, let's not consider carbon dioxide. Let's consider, not even glucose. Let's consider, okay, never mind. All right, yeah, we're going to go and consider, I'll tell you what, let's just zip on down to caffeine. Caffeine is my friend. We talk a lot. Hey, so carbon. How many carbons do I have here? 8. How much is each carbon? How much is the mass of each carbon? Yeah, it's actually 12.01 because we have to assume the average atomic mass, which is some carbon 12 and some carbon 14. So remember that that's average atomic mass. Hydrogen, how many? 10 of them, right? At 1.01 apiece. Nitrogen, I have 4 at, thank you for saving me from saying the wrong thing, 14.01 apiece. And then oxygen, 2 at 16.00 each. All right, so we're going to do a little math here, and then we're going to sum all those up. Okay, so do the math and sum them up. Let's see, what's that going to be? 96.08. 10.10. Ooh, 56.04 and 32.00. Add it all up. Oh my gosh. 6 plus 6 is 12. Thank you very much. All right. We get 164.22. Oh no. Let's see. 10, 11. No, I was too low on that. Mr. Willis, mistake. Is that not what, is that what, no, that's, yeah, that's, so 6 plus 6 is 12, 4, 1, 10, 11, 16, 17, 18, 19, 194? Better? Yeah. All right. So 194.22, again, grams per mole of caffeine. Percent composition by mass. All right. We are going to have to, I'm going to stop our class right there. I will continue in just a second with the rest of the discussion. At this point, I want to finish out our discussion today by talking about percent composition by mass, and that's going to be key. So let's think about water for a second, H2O. So if I ask you how much by percent of water is hydrogen, what would you say? And many students would look and say, hey, H2O, there are 2 molecules of hydrogen, 1 molecule of oxygen, that is a grand, or atoms, that is a grand total of 3 atoms per molecule, and 2 of them are hydrogen, 2 out of 3, and so you say about 67%. Okay, and so that would be what many people would say, and here's what I'm going to tell you. That is not what we're interested in. Okay, we are not interested in the percentage by composition, meaning the number of atoms, because that turns out not to really be very relevant. What we're interested in is the composition by mass. Okay? And so we need to say instead, we need to say, now here's what I want you to remember. All percents, any percent, anytime, anywhere, is a part compared to a whole. Okay, so the part of something divided by the whole of the amount, and that will be that. So what we need to know is we need to know the mass of hydrogen compared to the mass of the whole molecule. All right. Now remember, we've got H2O, and so we've got two hydrogens. All right, so I'm just going to say hydrogen. I've got 2, and that is times 1.01, so 2.02. And then oxygen, I've got only 1, but it is 16 times as massive as hydrogen. Okay, and so we've got 16.00. And so 1 times that, of course, is 16.00. Grand total then of 18.02 for the whole molecule. So when we say part divided by whole, we are going to say 2.02 is the hydrogen mass compared to 18.02 for the whole molecule. And that's going to reduce to right around 1/9, which will be about 11%. All right, so let's scroll down and see if that matches up. Sure enough, they did not use the exact value from the periodic table as I've asked you all to do. But 2 times 1 is 2, 1 times 16 is 16, and so 2 out of 18, sure enough, right there around 11%. All right, so percent composition by mass. Ooh, and I have heard some of you in your mind and quietly in the background saying, I don't know why Mr. Willis made such a big deal about that nomenclature stuff. What is he talking about, nomenclature? Nobody needs to know that. Here is the question for you. What percent by mass of, what is the percentage by mass of nitrogen in calcium nitrate? Uh-oh. What's the formula for calcium nitrate? Do you know? Can you figure it out? Because if you can't, you have 0 chance to answer this question. All right? Calcium is a +2. Nitrate, NO3, my polyatomic, it is a -1. We'll grab and switch those, cross them up, and we will have Ca, calcium, we'll have one of those, and then we will have NO3, we will have 2 nitrates. Now, so there's our chemical formula to begin with. And then when we do our percent composition, we need to know the part and we need to know the whole. The part, here's what I want to show you guys. How many, so let's just start here and work our way across. How many calciums do we have? We have 1, and it is going to have a mass of 40.08. So I'm going to say 1 times 40.08. That's not a negative. Next, nitrogen. And you might look and say, okay, I'm looking at the subscript. There is a 1, so we have 1 nitrogen. No. We have 1 nitrogen in each nitrate. But there are 2 nitrates. So 2 times 1 is 2, and each of those then is 14.01. And we'll get the value for that. Let's see, next, oxygen. There are 3 in each nitrate, but 2 nitrates, so that's a total of 6 times 16.00. And when I total all that up, I'm going to end up with 164. And so the total mass is 164 when we add all those up. And so we see total mass of 164. And so the question was about nitrogen. And so we remember that we need to, for any percent, do part over whole. And so you roll up and say, hey, what percent was nitrogen? What was the part that was nitrogen? Well, 2 times 14, so that's going to be 28.02. And so the part will be 28.02. Our whole is approximately 164. I'm not going to add that up right now. And when we do that division, we end up with 17.1% nitrogen. All right? And so that is how we do a percent mass. Again, just remember that percent is part over whole. And so you add up the total mass of the molecule, and then divide by the part that is whatever you're interested in. All right? Hey, hope that was helpful. Email or ask any questions, and we look forward to seeing you guys in class. Have a great day.